Hi and welcome back. So after this point we've discovered that you can create covalent bonds by sharing electrons and we've used Lewis dot structures to be able to kind of think about how we can get the electrons we need between the two nonmetals to form these covalent bonds. Today we're going to be talking about Lewis structures, how to basically take a Lewis dot structure and to generate a fully covalent molecule predictably. Okay, so let's start out with a restatement of our old friend, the octet rule. And this is basically saying that whenever you're making molecules and you want to make atoms happy, that you want to get them to acquire 8 electrons. You want to have 4 pairs of electrons surrounding all of your atoms, then they'll be stable. The exception is hydrogen. Hydrogen is up here, and we know from our electron energy shells that this one's in the first shell. It has only 1 proton, 1 electron, and to be happy, it can have 2 electrons. So let's kind of start this out, and let's maybe do an example here. So let's do NF3. So we can draw NF3, and if we wanted to see whether or not we could make this molecule, we could give everyone the electrons it needs for an octet. And so let's see here. So if I'm going to put 8 electrons around fluorine, we could do something like that. 8 electrons around fluorine, then we do that. 8 electrons around fluorine, that would do that. And that would give us 8 electrons around the center nitrogen. And this indeed would be a Lewis structure for NF3. So we could kind of redraw it that way. But this is kind of a haphazard way to do it. And so we're actually going to learn a series of rules that are going to help us always predictably, and I guess I should draw in the rest of these lone pairs, I apologize, predictably generate Lewis dot structures and get them right all the time so that we can take nonmetals, combine them, and form molecules with the correct structure. Okay, so let's learn some tricks that will let us always get these kind of problems right about generating a molecule from just the atoms. So let's say we wanted to make carbon tetrachloride, CCl4, and we wanted to know what the Lewis structure is, what the molecular structure of this is. Well, there's a couple of ways, some tricks we can do. So the first thing we're going to do is we're actually going to add up the total number of valence electrons that we have to work with. And so we have 1 carbon and 4 chlorines. And so if we look here, we've got carbon. This is our kind of condensed periodic table. We've left out a gap here. There's no transition metals. This is okay because we're only really working with the nonmetals in this case. And so we have carbon here, and carbon in this case is going to have 1, 2, 3, and 4. It's 4th position on the period. So we're gonna have 4 valence electrons. Okay, so we should have 4. And if we look at chlorine, chlorine is sitting happily over here in the halogens, and so if we're going to count from left to right, as we fill up our electron shell, we should see 1, 2, 3, 4, 5, 6, and 7. It's got 7 valence electrons in its outer shell. 1 more and it would be happy, it would be argon. And so in this case we've got 4 chlorines, and so we should see plus 7, plus 7, plus 7, plus 7. So our total number of valence electrons, this is kind of like our currency. This is all the electrons we have to do for bonding. It's going to be 7, 14, 21, 28, 32 electrons. 32 electrons. Okay. Next step. Determine the bonding of the molecule. So draw the molecule with 1 bond between each atom. Subtract the total number of electrons you used. So you can arrange these in any order you'd like, but often I'll put kind of the different atom in the middle. So in this case, we're going to do C, and we're going to make 1 bond to chlorine, 1 bond to chlorine, 1 bond to chlorine, and 1 bond to chlorine. Okay. Okay. So next we need to subtract the total number of electrons that we have left over, or we used from our total number we have. So we've used 8 to form these bonds, and so we're going to subtract 8 from this number, and that should give us 24 electrons remaining. And so place lone pair electrons around the outer atoms until they have the octets. So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we are good. We are really good. And this is a correct Lewis structure. And so we can redraw this if we wanted to with lines instead of those for the bonds. And then we can fill in the lone pairs as well if we want to. Okay, so let's try this for carbon dioxide as well. And so carbon dioxide is you're going to have carbon with 4 electrons, and then you have oxygen. Oxygen sits right here, and it should also have 5, 6. It should have 6. So 4 plus 6 is going to be 16 electrons total to work with. And so once again, let's put that carbon in the middle, and let's make a bond, and let's make a bond. And we have used 4 out of the 16. We have 12 left, so let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And everything looks good in the world except for the fact that this does not have its octet, right? There's only 4 electrons around that. So we don't have enough electrons to get our octets, and which means that we need to start making multiple bonds. That is the solution to getting a correct structure where all the atoms have an octet and you've used the correct amount of electrons. So let's kind of repeat this process, and what we'll do is we'll actually put double bonds there, and this now we've used 2, 4, 6, 8, so we have 8 electrons remaining. Now we have our octet on carbon because that has 8 shared electrons, and so let's finish the octets. Now that's an octet, and that's an octet, and this is the correct structure of carbon dioxide. Everyone has his octet, and we've used all 16 electrons. Okay, so let's do a couple more problems. Practice makes perfect. And so PCl3, phosphorus trichloride. So phosphorus sits right there, and chloride sits right there. And so we've got 1, 2, 3, 4, 5. So phosphorus has got 5 valence electrons, and chloride has got 7. So we have 7, 14, 21. 21 plus 5 is 26 valence electrons to work with. And if we kind of put this together as we would expect, starting with making bonds to everybody, that's going to be 6. So we have 20 electrons remaining, and so let's kind of give everyone its octet. And phosphorus needs 2 more to get its octet. Let's count up, see how we did. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Perfect, perfect. So we are good. This is the correct structure of phosphorus trichloride. Okay, so let's do one more problem, and that's NO2 plus. So remember, plus means that it's missing one of those negative electrons. And so when we're counting up the number of electrons we have to work with, the number of valence electrons that we're going to be able to use, we have to appreciate the fact that this whole molecule has one too few electron. That's what that plus means. And so we're counting up our valence electrons. Nitrogen should have 1, 2, 3, 4, 5. And oxygen should have 6. And so we should, in this case, should have 5 for nitrogen, plus 6 for oxygen, plus 6 for oxygen, minus 1 because we are missing an electron in this molecule. So in this case, we should have a total of 16 electrons to work with. And if we kind of begin our process and start with just a single bond for both of them, and then give everyone an octet, so we have 2, 4 there, so we should have a total of 12 more to work with, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be fine, except unfortunately that the nitrogen is missing its octet, So this is no good, so that if we don't have enough electrons to get octets, we have to start making multiple bonds. So let's go ahead and try and make a multiple bond. We'll start with just a single multiple bond in this case. So we've used 2, 4, 6 electrons. We should have 10 left to give everyone an octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How'd we do? The oxygens once again have octets, but once again this one only has 6 electrons around it. Does not have its octet, so we are still not right. Okay, let's add one more double bond, see if that's going to help us out. So now, there we go. Now nitrogen has all 8 electrons it needs around it. It's sharing all 8, but that's still fine. And we've used 8, so we have 8 remaining. Now we have oxygen, its octet, it needs 4 more. And this one needs 4 more as well. It's fantastic. That's exactly right. It uses 16 electrons. Everyone has an octet, and the whole molecule as a whole has a positive charge. So we're going to kind of put that little positive out there on the side. Okay, so in that very last example, if we wanted to be a little bit more accurate, we actually should have given the charge to a specific atom within the whole molecule, because some atoms in covalent systems or covalent molecules do possess charge. So this is a weird idea. This is not necessarily like ionic or covalent charge. We call this formal charge, and this is just to show that they are electron rich or electron deficient as to their normal state. And so when you're calculating formal charge, what you're going to do is you're going to look at an atom in a molecule. You're going to count up the valence electrons that that molecule would normally have. So for instance, oxygen normally has 6, fluorine normally has 7, boron normally has 4, carbon normally has 4. You're going to subtract the number of lone pairs on it from that, and then you're going to subtract half of the total bonding electrons, because typically you only give 1 electron when you're forming a bond. And if you have 0 as your answer, then you are uncharged. But if you have an overabundance of electrons, then you might be negatively charged, or if you're deficient compared to your valence electrons, you might be positively charged. And generally, when we create Lewis structures, that if you generate less formal charge is better. Because molecules are typically more happy when they're uncharged. And finally, as a rule, the total number of formal charges should always equal the total charge of the molecule. So in this example right here, NO2 minus, this is a negatively 1 charged molecule, which means that at most the whole molecule has to equal a negative 1 charge. And so let's kind of go through that example. First off, we're going to of course add up our valence electrons. Nitrogen, in this case, has got 1, 2, 3, 4, 5 valence electrons. Oxygen has 6. And so we have 5 plus 6 plus 6. And then we have an extra electron. That's what that negative 1 means. So that's going to be plus 1. And so in this case, we have 6 plus 6 plus 6 is 18 electrons to work with. And if we begin drawing our structure out here, let's kind of go through it. And we have used 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right. Is everyone happy? No, everyone's not happy. The nitrogen does not have its octet, and as a result, this is not a good Lewis structure. Everyone has to have its octet, and you must match the total number of electrons that you have to work with. So it doesn't have its octet. Let's make a double bond, and so let's make that one. That looks like a good solution. And so now we're going to give a octet to that one, an octet to that oxygen, and let's see, this one needs another lone pair, so it has 8 around it. So let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18. Great. This is a perfect molecule. This molecule is a good representation of NO2 minus. It's got 1 double and 1 single. Okay. And so let's before we finish up this problem, we have to recognize that there is charge on some of these atoms, and so let's kind of go through them atom by atom. So if we're going to start with this one, see if there's any charge in this one. We look at the number of valence electrons. Oxygen should have 6, so this first one is 6, and we're going to subtract the number of lone pairs. 2, 4, 6. So we've got 6 electrons as lone pairs, and then we're going to subtract half of the total bonding electrons. So there's going to be two electrons in that bond, and and we're going to subtract one of them away, and so this should give us a total of -1. So there we go. This oxygen has a -1 charge on it. That is where the negative charge of this molecule is residing. Okay, so let's solidify this with one last problem. And this is going to be the carbonate dianion. Okay, so this has got 2 negative charges on it, and so let's kind of build this one up. So once again, carbon should have 4 valence electron, oxygen should have 6, and so we're going to have 4 plus 6 plus 6 plus 6 plus 2, because we have 2 extra electrons there, and that's going to give us 24 available electrons. And so if we kind of construct this like so, and then give everyone a complete octet, and the carbon will need one in the center. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. To get everyone an octet, we needed 26 electrons, which means we did not have enough to make everyone have its octet. So let's redraw this with a double bond. All right, and so now carbon has its octet. This oxygen needs 4 more. This one needs 6 more, and 6 more. And so let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Excellent. This is a perfect Lewis dot structure. So let's kind of redraw it, clean it up just a little bit for us so we can see it a little bit better. Okay. And so we want to evaluate these atoms individually. And so I'll do one first, and we can see how this carbon should have 4 valence electrons normally. That's what it says right here. And then we're going to say it has 0 lone pair electrons, and it has half of how many total bonding electrons? It's got 2, 4, 6, 8. That's 8. So 4 minus 1/2 of 8 is 0. So this is a neutral carbon atom. It has no charge. However, if we were to ask the same question, for instance, of that oxygen atom, and so this oxygen atom has 6 valence electrons, we know that from right there, and it has 2, 4, 6, has 6 lone pair electrons, and it has 1/2 of 2 bonding electrons, and this is a -1 charge, and that's also a -1 charge. And so you can see that the answer, the real answer, is something like that. There's our CO3 -2, or our carbonate anion.